What is going on, everybody? Welcome to the Moment of Truth, as well as part 12 with the Python for Finance tutorial series. In the previous tutorials, we've worked on grabbing the data, we've worked on creating our feature sets, creating our targets, we returned our feature sets, our labels, in the data frame just in case, and now what we're going to do is actually do the machine learning, run it through a classifier, see what we get. So first of all, we're going to make some new imports here. We're going to come here, and we're going to say from sklearn import svm cross-validation and neighbors, and then we're also going to from sklearn.ensemble we're going to import the voting classifier and the random forest classifier. Whew, lots of information there. Just for the record, anybody who is interested in machine learning, understanding what the heck these classifiers are doing, you can come to pythonprogram.net, click on data analysis, go to machine learning, click on practical machine learning with Python, boom. And what this series does is it goes through each of the classifiers, explains what they do, shows a simple application of those classifiers, and then we actually write the classifiers ourselves in raw Python. So it's a really great way to learn about them if you want to know more. Otherwise, you can just do what we're doing here and not worry about it. Or if you already know, same thing. So basically SVM for support vector machine cross-validation, so we can create nice training and testing samples, because you don't want to test against the same samples you train against. You want those to be kind of blind. But you also want to shuffle your data. So cross-validation for that reason, neighbors, because we're going to do k-nearest neighbors, voting classifier, because we're not going to use just one classifier, we're going to use many classifiers and let them vote on what they think is best. It's a nice way to kind of smooth out any sort of unstable, I guess, classifications possibly, and in the case of having so much data, chances are that's going to be the case. Random forest classifier, just another classifier. Awesome. Now, going down to the bottom here, what we're going to do is create our new and kind of final function for doing machine learning, or at least typical machine learning, and that is going to be define do.ml, and we're going to check our phone. Do.ml, we're going to do ticker, and we're going to get our feature sets, labels, and of course the data frame, and we're going to do that with extract feature sets ticker. We're just going to copy that, come down here, and paste, and we don't need to run this anymore. Okay, so we've got our feature sets labels. Now we're going to create our training and testing. So it'll be x_train, x_test, y_train, y_test equals cross-validation. This, actually, cross-validation.train_test_split. Train test split takes x, it takes y, and it takes the test size, and we'll say the test size is going to be 0.25. So 25% of our sample data will be what we'll actually test against. This will give us our accuracy. Once we've done that, we're ready to actually create a classifier. Now, like I said, you can learn how to create classifiers and what they do and all that, but this is not what this tutorial is all about. So let's just define any old classifier. We're going to say we're going to use neighbors.k, neighbors classifier. So we've defined our classifier. Now we're going to say clf.fit the equivalent of .train. So we're going to pass xtrain and ytrain. Just again, so we're clear, xtrain is this data here, remember, and then obviously these are just changes, but that was then dfvals.values, that's what gets passed. X, this data is the percent change data for all of the companies, including the company in question. That's what this data is. Y is the target. It's 0, 1, or -1. So 0 for hold, 1 for buy, -1 for sell. That's our target classification. And what we're trying to do is use a classifier that will fit the input data to the target that we're setting. So let's see how we do. Right away, we can find out how we did. We can say confidence, well, not right away, it'll take a second for this to actually happen, but we'll say confidence equals clf.score, and we just pass x test, y test. And then we also, just because I want to know, let's see, confidence equals clf.score, we'll also grab, let's just do this too, predictions equals clf.predict. And then we'll just pass x test and y test again. Actually, sorry, just x test. So moving forward, if you train and you're happy with the confidence, all you have to do to further predict is literally do clf.predict. And if you wanted to not have to retrain this model again, you would pickle it. So using what you've already seen so far, you would pickle out the classifier, and then literally to use it ever again, you just load in the classifier, it's already ready to go, call it CLF, and then literally all you need to do is clf.predict. And that outputs the actual value. And you can pass either a single value here, or you can pass a huge list of values. It doesn't really matter. So in this case, we're passing a large amount of feature sets. And then it'll return to us a nice list of predictions. So those are our predictions. Now what we're going to go ahead and do is print predicted spread. I don't know. Something like that. Counter predictions. So we want to know, a lot of times with classifiers, you can get kind of overfitment or a strange issue where basically everything becomes one class. So this will happen often with imbalanced data because the classifier is going to realize, I'll actually get the best accuracy by always predicting a certain value. And so that can be very problematic. So you want to see, okay, what are the predictions that we were making? And we also want to see, are they skewed at all? Or like, because sometimes maybe not all of them are one, but like 99.9% of them are one prediction. So yeah, so predicted spread, we just want to know what's going on. So at the end of this, we can return confidence, but for now, we're not going to really do anything with that. So let's go ahead and do ML with, we'll do Bank of America. So cool, so let's go ahead and run that, see what we get. Hopefully no errors. So we see right away our spread, which is already imbalanced. It's relatively balanced by cell, but it's imbalanced. We did not print out accuracy. I'll yik yak in a second. Let's print accuracy here. I can't believe we didn't print. Let's actually say accuracy, confidence. Okay, try that one more time, and then I'll yik yak while we wait. So yeah, these are pretty balanced. This is relatively imbalanced compared to the other ones. And then accuracy, 0.377. So it's better than just, in theory, randomly choosing, but actually even randomly choosing would probably do worse than we did because this data set just in general is clearly more often a buy than it is a sell than it is a hold. And we do see our predictions at least somewhat model that. They do say, okay, a lot more. Actually, no, they don't. Huh. At first I thought they did, but no, we actually got a lot more sells than we did buys. And we still did better than average, which would be 33. Fascinating. Actually riveting. All right. But that's just a simple classifier. Let's see if we can do any better by actually coming up with a voting classifier. So rather than just this simple k-nearest neighbors, let's take 3 classifiers, throw them all at the problem, and then let them vote on what they all together think are best. So now we'll say CLF equals voting classifier. And then the voting classifier will take a list of tuples of classifiers by the name and the actual classifier. So first it's a list, and then the list will contain tuples of classifiers. We're going to have 3 classifiers. The first classifier is going to be linear SVC, so linear support vector classifier. So we'll just call this LSVC, and then we're going to call this svm.linear SVC. So we're just referencing that support vector machine for linear support vector classification. Default parameters. Next, we're going to do K and N for the K nearest neighbors. Again, we're just going to use this this exact thing right here. So I'm just going to copy, paste. And then finally, we'll add one more, and R4 for random forest. So random forest classifier. Awesome. So now we've got a new classifier. New classifiers in town. Let's see how we do. Save and run that. Come on, man. What do we got wrong here? I'm not seeing it. Is it? No. Dude. Might have to pause, so because I'm obviously blind here. Let me pause. Okay, so interestingly enough, it's actually up here that I messed up. Let me go ahead and reconfigure here because it's actually off screen. We'll just do 18, hopefully that'll fit. Let's see if it sure does. So, for some reason, the rest of this got deleted. So anyway, X, Y, and then 0.25 for the train test split. Okay, so let me try to run that again. Hopefully good. It must have happened when I deleted the other classifier or something. Singleton, array 0. What is wrong? Why are we getting all these errors now? I don't appreciate this. I guess maybe we'll have to add test size. It's probably corresponding to a different value, like a different parameter. And then while that's going, oh, looks at that. We got actually, we did improve pretty significantly there. Although we got way less predictions for a hold. Okay. Now, just for the record, there are a ton of parameters for each of these classifiers. I'm not going to get into them because, again, you kind of need to know how these classifiers actually work to understand the parameters. But for each of these, you have, especially with scikit-learn's kind of API on top of it, not only do you have like just the traditional parameters that you have in something like k-nearest neighbors, like k is a value. How many of k? We're using the default, which I think is either 3 or 5. But that you might want to change that. There's so many things that you might want to change with each of these. So we can almost certainly tweak this algorithm to be even more accurate than it is right now. But for now, what I'd like to do, also there's a whole lot more machine learning classifiers. These are just 3 that I just quickly made up. Not made up, but pulled out of my you-know-what. So the other thing I want to talk about is, okay, this data, unfortunately, this data is just simply imbalanced. It's not perfectly balanced, so that can kind of give us a little bit of a skew in our accuracy. So even though this looks pretty darn good, and we are still, this is fascinating, it isn't totally predicting just with this imbalance. It is making a slight change on this new data, and it appears to be accurate, interestingly enough. Anyway, there's a few things that are wrong here. I mean, possibly where we're predicting hold, we might be wrong because we didn't think it was going to raise more than 2%, but it turns out it did, stuff like that. You can also be wrong here, where you said, yes, it's a buy, but it didn't raise 2%, it rose 1.5%, but it was still a good buy. And same thing on the sell. But that can go the other way too, so you got to really pay attention to these. The accuracy is useful, but you really need to know what happens in practice. This is just not good enough. But I do want to, let's see if we can balance these numbers and still stay higher than 33% accuracy. So coming over to here, rather than using 0.02, let's see if we can't come up with some better numbers. So let's change this to be 0.025, and let's do this as 0.025. Let's see if that balances out the data a little bit better. Okay, yeah, definitely a little better. Not perfectly balanced, but close. And we're still about 40% accurate. Let's see if our predictions still real heavy on the down. This is for Bank of America. Let me pull up Bank of America. Because, well, no, that wouldn't make any sense because this is shuffled data that it's being predicted against. So it's fascinating that each time this shuffles, we're getting a different thing. Anyway, I wonder what's going on there. Okay, so we're on the right track. Still a little bit more buys than sells normally. So let's do 0.28, and then let's do this as 7. So 2.7 and 2.8. Let's see if we can get a nice balance here. That's pretty good. Basically about 1,400 of each. And again, still strong negative predictor, which is strange because I don't think Bank of America is doing horribly. Let's pull up the old Bank of America, shall we? Let's see. Okay, this is just recent, but yeah, it's weird that so often we predict a drop. Oh, wow. Yeah, that's a pretty... I guess the old recession hurt some people more than others. I know you guys feel so bad about the banks, right? Okay, so, yeah, so cool. That's interesting. And I wonder... I'm sorry, I really want the training to be perfect. I'm finding it interesting that we're able to balance this spread initially, and then it gets shuffled, and then somehow it's imbalanced. But whatever. Still mostly predicting -1. Interesting. I wonder if there's some sort of issue here that's causing that. But I'm going to go ahead and move on from here. We'll leave that in the dust. Because basically at the end of the day, you can get these answers, but the question is actually how good do we do in practice? Not just how good is our classifier. Everything changes when you actually go into practice with one of these and actually trade on one of these. Because your accuracy suddenly doesn't matter as much as you might think. So anyways, that's it for now. If you have questions, comments, concerns, whatever, feel free to leave them below. In the coming tutorials, what we're going to be doing is taking this data and learning how to do backtesting with it. I thought about doing deep learning with this data because in the current situation, it would be pretty quick for us to throw in a deep neural network into this. But I think I'm going to leave that out. If you really want to see it, feel free to let me know. Maybe I'll throw one in. It's almost certain to give us the exact same accuracy. We just simply don't have enough data to do deep learning and do it right. We would need a whole lot more data than this. But it could give interesting results. I don't know. But for the most part, when I play with deep learning with a data set as small as this one is, it's just, there's no fruit. So anyways, we're going to get into actually back testing it and actually seeing how would a real strategy deployed in the market do. So that's what you guys have to look forward to. Questions, comments below. I'll see you next time.